Hello folks, we are now doing the exercise 7.5. In the last video we completed the exercise 7.4. Now we are into the exercise 7.5. Now the 7.5 exercise, integration is by partial fractions. Okay, partial fractions means we'll have these factors in the denominator. Depending on how the factor is, we have to express the entire fraction in a particular form. For every type of factor which is there in the denominator, there is a different expression. So accordingly we express and then we do the integrals. That's how it's going to be like. So as every type comes, I will tell you what is the substitution so that we don't get confused by taking everything together. Now here we have got two linears in the denominator. So whenever you have two linears in the denominator, we go in for a substitution A over the first plus B over the second. So that's how we take up. There is, as I told you, for everything there is a particular way of substituting. So for this it is going to be that way. So this one, so consider, that's how we are going to do it. Consider x over x plus 1 times x plus 2, because we know that having a product in the denominator and then yet another number in the numerator and yet another term in the numerator, it's quite clumsy. We are not able to do the integration. So that is why we are trying to find out a method by which we will have two fractions which are very easily integrable, and then we are able to get the answer. That's what we're going to do. So therefore this, whenever you have these two linears in the denominator, we are always going to express it as a over x plus 1 plus b over x plus 2. That will give you the answer. Now how? So let's equalize, because we need to equalize. We know that this entire fraction will be multiplying by x plus 2 and this entire fraction will be multiplying by x plus 1. So this entire fraction we have multiplied by x plus 2, this entire fraction we have multiplied by x plus 1, which has made both the denominators. Here it will be x plus 1 times x plus 2, here it is x plus 2 times x plus 1. Net effect, both the denominators are same. So we write a common denominator. When we compare it with what we have written here, we come to know that denominators on both sides are equal, so they can cut each other. As a result, we are left with x equal to a times x plus 2 plus b times x plus 1. Now in this method, that is method of partial fractions, it is for us to find out a and b. If we can find a and b, then our entire, this expression will become this kind. That's a linear in the denominator, is always having log as a integral. So that will become very easy. Once you have got a and b, your work will be easy. So it's our work now to get a and b. And in order to get a and b, what we do is generally we look at the linear factor which is there here, x plus 2 and x plus 1. We make substitutions. Like for example, first time we will make a substitution x equal to negative 1. Why? Because we had the plus 1 there. Our idea is to eliminate one term so that we will be able to get a and b easily. For example, if we take x as minus 1, then look at what is this expression. It's minus 1 equal to minus 1 plus 1. This term is gone. There is no b term. There is only this a term. So it is a times minus 1 plus 2, which is 1. That way a becomes minus 1. So you have got the a value. Now to get the b value, substitute x as negative 2. So if you substitute x as negative 2, let's check what happens to this expression. Negative 2 plus positive 2, this expression has gone like the previous one, but only this expression is surviving. B times negative 2 plus 1. So that's going to be negative 1. And that, both the negatives, when you cut from the other side, you're going to get the b value as 2. So that's exactly what we want for our integral. So our integral I has now become, instead of x, see, we have told this as this, isn't it? So instead of this expression, let's write a, which is negative 1 over x plus 1. We can take it from here, you can see it. And b is 2 over x plus 2. So much simple now. Why? Because both are linears. Linears in the denominator is log. Okay, because 1 over x is log in the integral. So therefore this is negative 1 over x plus 1 dx, and here 2 can go out, dx over x plus 2. So that's really easy. This is negative log x plus 1, and this is 2 log x plus 2 plus c. Maybe you can take it as a quotient so that this becomes log x plus 2 the whole squared and all that. Yeah. Negative log x plus 1, if you want, you can call it as log x plus 2 raised to 2 if you want, plus c. That's it. Now, I'm wondering whether we can leave it like this or should we simplify. Of course, simplifications are possible. This is how it is. Let's go in for the next one. I equal to integral of dx over x square minus 9. Now this is also quadratic, so but then we have to check how like will it break into factors and things like that. X square minus 9 dx. So we know x square minus 9 is of the type a squared minus b squared, which always breaks as a minus b into a plus b. So x minus 3 into x plus 3. So it's of this type only. Now if you have two linears in the denominator, then you have to make this substitution. So maybe let's consider 1 over x minus 3 and x plus 3. We have learned from the earlier one that if you have two linears in the denominator, then you can write a over the first and b over the second. So when we happen to simplify this entire thing to be multiplied by x plus 3, this entire thing to be multiplied by x minus 3 to have the denominator same. So here it's going to be a times x plus 3 and b times x minus 3. Like that, you have both the denominators equalized, and in that process you have these two denominators cut also, so that you are left with 1 equal to a times x plus 3 and b times x minus 3. It is for us to find out the a and b value. So if x is negative 3, then this term is gone. So what happens? This term is gone. So b times negative 3, negative 3, negative 6, which is 1. So b is minus 1 over 6. So also if x is 3, then what happens? If x is 3 means this term is gone. 3 minus 3, 0. This whole term is gone. You're left with a times 6. 3 plus 3, 6, which is 1. So a is 1 over 6. That's it. That reduces our work. Now let's see what is I. I for us is we can take this hint from here. Yeah. So instead of writing 1 over x minus 3 times x plus 3, we can write it in a and b form. So a for us is 1 over 6 times x minus 3 dx if you want, and plus b is a negative. So negative dx over 6 times x plus 3. You can just check, okay, because it is minus 1 over 6. That's how the negative has come. Now this is quite easy because 1 over 6 can go out, dx over x minus 3. And here also 1 over 6 can go out. In fact, 1 over 6 can go out throughout. I think that's better. We can have it fully going out, so that we don't have to write it every now and then. Dx over x plus 3. Now when you take the integral, it will be 1 over 6 log integral of x minus log modulus x minus 3 minus log modulus x plus 3 plus c. Now this, because it is negative, you could write it as division. So if you want that, we failed to do that division. Actually this we could have done here also. This would have been log modulus x plus 2 the whole squared, because it is minus log, so it can be written as modulus of x minus 1 plus c. Further, that was a further simplification step here, because it is minus here, so it's log modulus x minus 3 over x plus 3. And this 1 over 6, either you can write here or you can write it as an exponent plus c. That's it. So that's what happens with our next video. It's an exponent, isn't it? So it's fine if you raise it or you write it here. Both ways it's good. So that should be all for this video. This problem number 1 and 2, where we have done partial fractions. We have learned that if there are two linears in the denominator, then we are going to write it as a over the first plus b over the second, find out a and b and get the integral. So we'll continue with this. I don't know what is going to be 3 and 4. Depending on how many factors are there in the denominator, we make a different substitution, right? So with those problems, let's meet in the next video. Thank you.